is not in your textbook, and that's why it says supplement, because all the information on linear regression will be given to you right now in this packet. These sections here, 2.3 and 2.4, are on lines and slope, which should be review for everybody in this class. If it's a little ancient to you because it's been a while since you looked at it, I will quickly review it as we go through the class demo today. You'll also have some practice in your class activities. Okay, but the main idea for reviewing this is so that we can ask questions. Don't take that just yet, please. So that we can ask questions and answer them for our regression part of the class. So let's start off with the demo. And Joshua, you want to read us number 1, please?
In 1989, 44% was on a weight loss diet. In 1990,
if we measured time in years since 1987, so that's how we're defining one of our variable, it's going to be in the number of years since 1987. We're kind of used to this by now. Translate the given information into 2 points. So what we want to think about is that if we were graphing this, we'd have a variable along our horizontal axis and a variable along our vertical axis, and we want to look at that information and try to determine which variable would go where. So anybody want to help us with this? Which variable would you put along the horizontal axis? The time, the number of years since 1987 or after. Okay, this is what we call our independent variable, because the value of the percentage of the population on the diet depends on what year we're looking at. And then that only leaves the percent of the population on the weight loss diet as our vertical variable. We call that the dependent variable, because its value depends on whatever value of x I put into this particular equation once we get it. Okay, so I need to come up with 2 points to define a straight line. Okay, I need to come up with 2 points. Where do I get the 2 points in my information given? Can someone help me where I get the 2 points?
1989 and 4%.
Right, so right here, if we look at that, we get 2 values of our variable. 1989 tells us how many years, well, it doesn't tell us, we have to figure it out, but it does give us a point in time. The 44% tells us the percentage on the weight loss diet. And where else is there another point? Right, 1997 and 12. So we have to convert those 2 points, or that information, into 2 coordinates. So 1989, if we were to convert that information into 2 coordinates, what would be the values of the coordinates here, both the horizontal and vertical coordinate? 2, 44. And we have 2 because 1989 is 2 years after 1987. Okay. Notice I don't say 0.44 because we're saying that the vertical axis is the actual percentage, 44%. And so our second point would be 10, 12. So we know we need 2 points to make a straight line, at least in Euclidean geometry. So let's say this is 2, 44 and 10, 12. So once I have 2 points, there's a unique straight line that I can draw between those points. So let me just draw quickly a straight line through those 2 points. There we go. And now to get the equation of this line, we need 2 bits of information. We need to know the rate of change between those 2 variables, which we call the slope. And we also need to know where would this graph intersect our vertical axis. That's called the y-intercept. So let's find the slope first. And a quick review of the slope is that the slope is the change in our y values over the change in our x values. Another way we could write that is delta y over delta x. That little triangle is the Greek letter delta, which means change in. It does not matter which of these 2 points I call x1, y1, x2, y2. It's totally up to you. I usually just start with the first point and call that x1, y1, and the second point x2, y2. So I subtract my 2y variables. The order that you subtract doesn't matter as long as you keep their partners, the x values, in the same order in the denominator. So let's say I start with 12, and I'm going to take away 44. And the only important thing to do is that 12's partner, its x coordinate, is the very first part of this subtraction problem on the bottom, 10 take away 2. Now, you'll always be asked, probably throughout this class and in your next project, to interpret the slope. So a really good idea when you're creating the rate of change here between your two variables is to actually put in your unit. So you could just put it, just to save a little time, you could put that in parentheses and put percent after it. You could put that in parentheses and put years after 1987, because now when you go to interpret it, it will be looking at you right in the face. So 12 take away 44% is negative 32%, and 10 take away 2 is 8 years after 1987. So you could interpret that slope just as you see it. You could say that 8 years after 1987, there'll be a decline in the percentage of people in this country who are on the weight loss diet by 32%. But usually we like to talk about slopes in a way where it's what we call a unit rate. Now, the reason I'm using the word rate is a rate is just a ratio, like this, of two numbers, where your variables that you use, your units are different. So I have percentage in the top and years in the bottom. So that makes it a rate. We usually like to have a unit rate where the denominator is 1. It's a lot easier to interpret and discuss. So we can reduce this particular rate to this, negative 4% over 1 year after 1987. You just reduce your fraction so you have a 1, or your rate, so you have a 1, which is called a unit rate, and then it's a lot easier. It's not as cumbersome to talk about. So someone want to give that a shot? You want to interpret the slope as a rate of change in the context of this story. So in the context of this story, we want to make sure we use both numbers that we see here and both units. So I want to give it a shot, Josh?
On average, 4% of the population each year drops off the band.
Okay, 4% of the country's population, 4% of each year. The only thing I'm going to add to that, Josh, is each year after 1987 drops off the bandwagon. All right. Now, if I read that, because I read the original story, I know what Josh is talking about. Dropping off the bandwagon, probably you could say deals with that negative in front of the 4%. Because you've got to get an English word in your sentence somewhere that's going to describe that negative in front of your 4%. Someone else want to maybe do it a little differently? What Josh said is fine. I would understand what the negative 4 divided by 1 would mean in the context of this problem, the story. Someone else? Since Alex isn't going to yell at me for calling it a story. Yeah, go ahead. Okay, on average, 4% of the country's population stops dieting. The only thing I don't see here is this part right here, the per year. So we have two variables. So you can keep going. Every year when? Perfect. Yep. Every year. Good. You have to see both variables, right? the time, and the percentage. Every year after 1987, right. We're all individuals. We would probably all, if there's 20 or 24 of us in the class right now, we'd probably write 24 different sentences. Okay? Any questions on interpreting the slope as a rate of change? So the slope as a rate of change, if you want to read more about it, is section 2.4 in your textbook. 2.4. The stuff we're about to do with straight lines is section 2.3. Okay. So we really have three forms of, three different types of equations to represent a linear relationship. We have this form, we have this form, and we have this form. This is called our general equation. And if you see a relationship, a linear relationship written like this with your x and y variables on the left side and a constant on the right, it's really handy dandy for getting a quick graph of that equation by using your intercepts. If you use your x and y intercept by plugging a 0 in for x and coming out with your y value of 2, there's your x-intercept. And when you put a 0 in for y and you get x is 3, you have your x-intercept. Voila, you have two quick and easy points to draw a straight line between. So most of us, if I ask you about what's the equation of a straight line, there would be the chorus effect, I call it. Everyone says y equals mx plus b, as if that's the only equation for a straight line you've ever seen. But this is the most popular one. Okay, this is called, you know, the slope, and b represents your y-intercept. So from that, we get the name of this equation, the slope-intercept. So this would be the slope-intercept equation for a straight line. Okay. The third equation is really very useful, but probably one that students tend to shy away from. And it has the slope in it as well, but you also see placeholders for a very specific point, x1, y1, and that's a point that lies on your line. That's a solution to your equation. So because we have the point x1, y1 in this equation, this is called the point slope equation for a line. Okay, so we're going to look at all of these today. Some of these will be in your class activities, but those are the three forms of a line that we tend to work with. Okay, so let's work first with the slope-intercept form of a line, y equals mx plus b. So find the slope-intercept form of the equation of a line that models the percentage of adults on diets X years after 1987. So we can fill in a part of this right now without a whole lot of effort. What part of this can I fill in right now? Slope, right? Which is what? -4. Okay. So now I'm sort of stuck a little bit, right? Because right now I have an equation and I have to solve for b. And the only way I can solve for b is if a little birdie comes and sits on my shoulder and tells me a value for x and a value for y. That would be a point that lies on that line. Okay, so I happen to know 2 points that lie on that line. I know the point 244, is that right? And 1012. Doesn't matter. I'm just going to pick 244 just for the heck of it. This is my y value. This is my x. I put 2044 in for y. And when y is 44, x happens to be 2. And now I solve that equation. I add 8 to both sides, and there's my b value. So now you just have to remember to put all your information together. There's one more step to write this equation in slope-intercept form to look like this. All right? So that's slope-intercept form. When you look at that equation, you get 2 bits of information directly staring at you. You can look at that equation and you know what your slope is, -4 divided by 1. And so you can interpret that. And then you also know your y-intercept is 52. So let's talk about what the y-intercept means in the context of this particular problem. So it always helps for you to write down the coordinates, 0, 52. Once you do that, if you then put in the actual units, 0 means years after 1987, and 52 is a percent of the country's population on a weight loss diet, but I'm not going to write all that because I'll be writing it in a minute. The minute you put those units in, you can actually then go right into your complete sentence to interpret it. So someone other than Josh, and who gave me the other one? I forgot. Carlton, you want to do this one? In 1987, 52% of the country's population was on a weight loss diet, right? Perfect. Okay, no problem. Again, where does the 0 come in? Right here, 1987. That's your, since you're starting in 1987, that's going to be your y-intercept. And the 52 is right here with its unit, the percentage, and it's the percentage of the country's population on a weight loss diet. Any questions on interpreting or finding this equation before we move on? Anything at all? All right, so we can now look at the same information in the point slope, and the only difference is you literally put in the point right now. You put 44 in for y1. Your slope is -4, and x1 is 2. So you put it in right at the beginning. You solve your equation. Well, there's not much to solve here. You could actually leave it just like this. There's nobody's saying you have to then take this equation and solve it for y so it looks like part D. This is legitimate right here. And why this is nice is you can look at this and you can tell me something right away. You can tell me what the slope is, and you can give me a solution for the equation, 244. You know that that point lies on that line just from looking at that equation in the form. If you take this equation and you do what we're about to do on the very next page, you put it back into that form, you lose that visual of seeing the point, one of the points that lie on the line. You see the other point, you see 0.52. So you can convert this equation to slope-intercept by just doing a little bit of algebra. So it's y take away 44 equals -4 times x minus 2. So basically, you just solve this equation for y, and you get right back to the equation we had in part D. So this does agree. Yes, it does agree with the equation in part D. And now, whether we can now use this equation, the equation solved for y is very handy when it comes to answering either estimating values of the percentage of the population that's on a diet or predicting. So when it's in this form, it's very easy to answer questions like H and I. Okay, so let's take a look at this form of our equation and predict the percentage of adults on a diet in 2000. So we're predicting the percentage of adults. That's our y. So we're going to predict this, and so we're solving this equation for y. So that's what we're doing, solving for y, which is kind of cool since our equation's already set up to equal y. So the only thing I need is a value for x. So what's going to be my value for x here? 1987, 2000 is 13 years beyond 1987. So where I see x, I put a 13, and voila, I get y is 0. What do you think about that? Huh? You think that's going to be you think that, well, let's take a look at our data real quick. Where does our data begin and end? Our data begins, if we go back here, oh, I didn't give you the data, right? The data is right below this. Our data begins in the year 1987 and goes to the year 1997. So if we were using this model, we'd say 2000, 0% of the population is going to be, we'd be going beyond our data set, we'd be extrapolating. Most likely that's not going to happen. So this would be another example of what we looked at way back in the beginning of September of a model breakdown. That's what this model would predict, but it's probably unlikely. So I would say that this is an example of model breakdown, that 0% of the population is not on a diet. Even if it was for medical purposes and not weight loss, well, we're just looking at weight loss, right? But you could be on a weight loss diet for medical purposes. So there's always going to be some percentage of the population on a diet. Okay, so now we're asking a little different question. We're saying, in what year was 50% of the country's population on a weight loss diet? So now what we're trying to solve for is we're trying to solve for X, the year. So this 50 is the value for Y. So we put that into our equation and we solve for X. So we get X equals positive 1/2. When we do the algebra there, we subtract 52 from both sides and we divide both sides by -4, we get 1/2. So we would answer this by saying halfway between 1987 and 1988, 50% of our population was on a weight loss diet. Okay, so you can fill that in later. Any questions on using the equation of a line to either make a prediction in the future or to estimate a value for your independent variable? Any questions? All right, so now we're going to talk about where we're going with linear regression. So with this data that I just gave you, we can assume that as we go from one year to the next, beyond 1987, our rate of change and our percentage of the population that was on a weight loss diet is constant. It never changes. And you see that by looking at this ratio of -4 to 1. And it doesn't matter what 2 points you go between. If you looked at 4 to 8, that is a change of 4 years. And the corresponding change in percentage is a decrease of 16. Notice that that's the same as the ratio 4 to 1, -4 to 1. So this constant rate of change is what makes a straight line totally straight. So if we took this line and we took these points and we put a line between those points, you would see that the line goes directly through every single point. There's no lines that fall, there's no points that fall above the line or below. We say that this has a perfect correlation. Now this term correlation has a special meaning when we talk about linear regression. We're going to get there in a minute. When you have perfect correlation, that's the ideal, that's the utopia of fitting real world data to a straight line. Chances of it happening, pretty close to 0. But to get exactly a correlation where everything lies in a straight line. Okay? But you can get things that lie close to this line. So for example, let's suppose I said this is really what the data would look like. If I went out to this particular country and I actually took a look at the percentage of the population that's on a diet, weight loss diet, in these years after 1987, you see I get a scattering of points in this plane. Okay, they look like they kind of follow a trend that as my year increases, my weight loss percentage decreases. And if I sort of drew an oval around these little points here, it would be kind of a tight oval of some sort, you see, something like that. So it looks like it has a trend, a downward trend that is linear. When you see points like this, then you say, haha, these points may be able to be modeled with a straight line. Okay? They may be able to be modeled with a straight line. One of the ways that you model something with a straight line is first you look at the points, and this is called a scatter plot because these points are scattered all over this plot. So you look at the scatter plot of your points. And to do that, I'm going to bring my graphing calculator out and show you how you would do this on a graphing calculator. So I want to make this a little teeny bit smaller. Oops, come back out, just a little smaller. And don't worry about getting this all down right now because it's every single step is written out for you in your packet. So I just want to show you how you would do this on a calculator. So you turn it on first. And I'm just going to clear everything out. And I go to my stat button because the test for calculating this line, the best line that fits through that data is a statistical calculation. So I go over to calc. But before I do that, I have to enter my data. I can't calculate any tests unless I enter my data. And the data is entered right here in number 1. This stands for editor. So you go in. And you have all these various L1, L2 columns. So I'm just going to go here and I'm going to clear out that. I thought I could clear out that column. There we go. So let's go over here and let's enter these first points here, 0 through 10. So you do 0, enter, 1, enter, 2. Isn't this fun? You get to watch me enter 5, 6, I know, 7, 8, 9, 10. Okay, so we've done that. And now we're going to go up and we're going to enter L2. Could someone read those to me so it'll be a little quicker? 57, quick. 52, thank you. Yep. Yep. Okay. 26, 24, 16, 20, 12. Thank you. All right. So I've entered my data into those two columns, and you have to remember the name of the two columns, L1 and L2. And I want you, when you get your calculators, you'll see right above the number 1 key, you see a little yellow L1. That refers to this list that I just put in, the L1 column. And right above the 2 key, you see a yellow L2, and that refers to that list of data. Okay? So if I wanted to take a peek at this data, just like you see here, there's something called a stat plot. You got various plots you can look at in statistics. So because that's yellow, you hit your second button, y equals, and let's say we want to put our stat plot on for this data. So you hit enter to say, okay, all of these are various stat plots you can get. The first one that's always highlighted as a default is your scatter plot, which is all you're going to need in this class. Notice your X1 and your L1 and L2 are your default list. Perfect. So there's not much to think about. Now to look at the graph, you just hit zoom 9, which gives you your scatter plot. So if I gave you a bunch of data and you plotted it and it looked like that, you say, yeah, that looks like I can get a line through there pretty easily. Okay, without too much trouble. So one of the things we have to think about is, well, you could pick any 2 points to put a line through, right? We put our line through at the beginning of class, the point 244 and the point 1012. And as you can see, that straight line, if I chose that as my line to model this data, there'd be several points above the line, several points below the line, a couple of points directly on this line. But the question still remains, what would be the best line that would actually fit this data the best? And what do you think we mean by fit? That's an interesting question. And if we take statistics, I could show you that, and if you're interested, I could show you later. I was doing it for my first class, and I think I gave them a little too much information. But basically, for our purposes, we want a line that's as close as possible to all those points. So we're always going to get some points above this line and below this line, but we want the vertical drop between the point and the line to be as small as possible. Okay, so if I asked you to pick 2 points and draw a straight line, given that there's a number of different students in here, we could get any one of these lines on this graph. Some of them you can see are much closer to the data set than others. So the question arises, how do I find the line that's best? And in statistics, or calculus, you can actually go through the mathematics of finding this line. And in fact, when I was in college studying statistics, we never had graphing calculators, so we had a group by brute force go through all of the calculations to come up with what your calculator is going to give you instantly, or GeoGebra is going to give you. So in Project 3, you're going to see how to use GeoGebra. I can show you as well. It's much quicker with GeoGebra than the graphing calculator. The equation of the best fit line or the regression line is graphed below. So we put all of this data into our calculator, and I want to show you how we get the equation for this line from our calculator. So we've entered our data, we've looked at our scatter plot. Now we go to stat. Again, don't worry about this, it's all written down for you. You say calculate, and you want a linear regression. Notice you have a linear regression here, and if you go scroll down a little bit more, you got another linear regression. And the only difference is they just reverse the AX and the B. And the reason for that is usually when most people in statistics use the regression, you always start with the point, like with the company, like, or a fixed cost. Like when we say, I got a fixed cost, and then my cost increases $4 every text or something, you start right there at your fixed cost and go up. A lot of times in stats, they like that beginning point first. But in algebra, because we're so used to the mx plus b, we tend to use that model, where a is your slope and b is your intercept. So it says, I'll find you the best line. Tell me where your data is hidden. It's in L1 and L2. So you hit second L1, comma, second L2, comma. And now this is the hardest part of the whole thing. You got to tell it to store your equation in one of your Y1, Y2, or Y3. So there's a couple of things you have to press. You can't just press Y equals, unfortunately. You have to tell it to go to the Y variable, to this button. So there's this button right here called vars. So you hit vars. It's all written down, don't worry. And you want it to be in the Y variables, the Y vars. And then you hit enter, and then you pick one of those Y variables, Y1, Y2, Y3. I'm just going to hit Y1. Then you hit enter, and voila, there's all your information. You have your slope, negative 4.3, which we've already seen, and your y-intercept is 53.95. Now that's different than our first equation, which was 52, because that's where everything dropped by 4% each year. So this is the equation that models this data. It's the best equation. So I would label this as y hat equals negative 4.3x plus 53.95. Why do I put a little hat on it? Because that reminds me that I'm predicting values using this model. Okay, it's not the actual data values, it's a predictor. Now this R value right here talks about the strength of the linear fit, the strength of the linear association, how well this line, these two coordinate, excuse me, I'm talking too fast because I'm looking at the clock. These two variables, the strength of their linear association, that's what this correlation coefficient, which we use this letter R for correlation coefficient. How strong is this linear association between these variables? And the negative just tells you the direction. That just tells you the direction, that as your x variable increases, your y decreases. But the fact that this is pretty darn close to 1 tells you it's a really, 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 really strong fit. Okay, strong association. So remember, a correlation coefficient tells you the strength of the linear association between two variables, two quantitative variables. Quantitative variables. Okay. So we can, the strongest association we can have on the negative side is -1, and on the positive side is a +1. So R will always float between +1 and -1. And depending on how close it is to 1 is how strong you can say the relationship is. As you get close to 0, it's pretty crappy. Now, my pictures didn't translate like they did on your lecture notes. So the one I want you to pay the most attention to, we've already looked at an R value of -1. An R value of +1 is just the same exact fit, but it's going in a positive direction, the slope. The pictures you have for the next two show you a good positive correlation and a good negative correlation, fairly strong. But this last picture, I think if I was looking at your notes, would look something like this. So when it's just this cloud of almost circular points, there's no direction indicated here. I could drop a line this way, up and down. There's nothing here that helps me. So we would say this correlation coefficient would be pretty close to 0. So that's not good if you have a correlation coefficient close to 0. So that's about all you need. I do want to show you quickly how easy you can get the same information from GeoGebra. So when you start your class activities today, I want you to go to number 8, and I'll give you a graphing calculator, because if you have any questions in following the directions, I want you to be able to ask now instead of when you get home. And also, I want to show you quickly how you do this on GeoGebra. So GeoGebra, you need to have all views up. You need to have your algebra view, which you see with this little blue rectangle in your spreadsheet. And we only need 2 columns to put our information in, so I'll just squish this over like that. And let me show you how easy it is to put the data into GeoGebra. When your data is 0 through 10, you just put your 0 in, and if you know how to use spreadsheets, you can go like this, equals this cell, A1, plus 1. Or you could literally put every single value in, but once you have that, you just take it and go down like that, and there's 0 through 10, all done for you. Now we put in the actual percentage from the population. I need someone to read it to me again. It was 57, next one. 54, is that right? 52, yep. 44. What? 38, and then 2 36s? 2 34s, okay. 34, 34, 26. Come on. Yep. Come on. Come on. Yep. Yep. All right. All right. Then to get your scatter plot, all you do is you just highlight those values, click right and say create a list of points. Voila, there's your list of points in your algebra view. And you say, wait a minute, I don't see my scatter plot. Why not? It's not the right window, right? So you just move that a little bit and you scrunch it down, and voila. Instant scatter plot, all done. To get your line of best fit, you have fit line is your command, and then you see those little brackets right there, fit line. You just squeeze in there, you put your cursor in there, and you say list 1, and there's your line. Voila. And not only do you get your line, but you get your equation. But notice your equation up here is in the general form. It's not solve for y. Yuck. You can solve it for y if you want, or you could right-click and say, hey, I want it in my y equals mx form. Voila, there you go. Same exact answer we got with the calculator. If you want your correlation coefficient, your command is correlation. Spell it right. Ooh, good. It knows what I want. And then I go in there and I put list 1 again. Voila, there's my correlation coefficient, negative 0.98. Okay, so GeoGebra is very quick for getting this. Your calculator is actually very quick as well. It's just that one part where you have to store it in the Y1 or Y2 that is really the part that most students forget, and they've got to rely on their notes. So I'd like you to start with number 8. I have graphing calculators up here if you don't have one, and then you can move on to looking at some of the review we have with the straight line stuff. And many of you will hopefully be able to work through that pretty quickly.